Hello students, this is Rajiv back again. So in the videos which I uploaded a couple of days back, we have discussed about a good portion of the first chapter of class 11, right? So we talked about at a high level what physics is. We went over to discuss about physical quantities, right? How physical quantities are expressed in terms of magnitude and unit, right? Numerical values and unit, and what is the meaning of magnitude. We also talked about the most prevalent units, right? The SI, the MKS system, the CGS system, the FPS systems, and all. We came over to dimensions, right? We deduced dimensions of some very simple physical quantities. And yes, the intention why I am not intentionally introducing a lot of physical quantities and their dimensions in this videos are because I still remember till the end of my intermediate, if somebody would have asked me what was the most difficult chapter in physics, I used to say units and dimensions. I understand now when I listen to that, that sounds very funny. But then yes, I was just fresh from class 10th, and obviously when I heard so many new terms, right? In my study up to class 10th, probably force, pressure, density, velocity, these were common terms for me. But obviously the moment I started seeing Young's modulus of elasticity, and a lot of other things, right? Boltzmann constant, van der Waals gas equation, things sounded very overwhelming for me, and I got scared of them. So intentionally for my students, I have limited them to the very well-known physical quantities to start with. And our strategy would be, as we move into any particular chapter and we talk about any particular physical quantity, obviously, we would be pausing for some time and talking about the corresponding units, dimensions, and things of that nature, right? And today, in this video, we will continue our discussion into the dimensional analysis and the uses of dimensional analysis. The first use we have already seen, that was using the principle of homogeneity, how we can establish whether an equation is dimensionally correct or not. And we have understood that if there are, in any equation, the physical quantities are separated from each other either by a plus sign, a minus sign, or equal to sign, right? So if we have physical quantity P1 minus Q1 plus Q2 equals to, if it is PQ3, then the dimensions of each of these quantities must be same. Similarly, if it is NP1 or NP1 into P2 into Q1, so which obviously mean each of these physical quantities should be dimensionally same, or else we cannot establish that as an equation. Or we have also seen that, that's why we can say 30 liter plus 20 liter equals to 50 liter, but we cannot say 30 liter plus 10 Newton equals to how much? This is a wrong question, right? Because this is length, this is force. They are not dimensionally same, so they cannot be added or subtracted in an equation. So we have covered up to here, and today what we would look into would be the other use of dimensional analysis. Okay, then we would take we would step back a little bit, and I would introduce about the prefix table, right? So prefix table, and then we would move on to rounding off. Okay, we would then go over to your order of magnitude, and we would then move on to your significant digits, and this is where we would end our chapter 1. Errors in measurement intentionally I'm not discussing here because again, as I said, my intended audience are class 11 student. So until and unless they have actually gone into a physics lab and have touched either a slide calipers or a spherometer or any of the apparatus, until unless those terms are very common to them, the list counts and things of that nature, I don't want to introduce the errors in calculations over here. So I would not talk about that right here, strategically. Okay. So let's move on, students. So let us resume uses of dimensional analysis. Right. So the second use of dimensional analysis is to convert magnitudes in one unit into other. Okay. So convert, right, the numerical values expressed in one unit into other, right? So for example, if I say mass of this pen, okay, when I say mass of this pen, obviously my physical quantity is mass, right? And if I'm saying mass of this pen is 100 gram, okay, and if I say how many kilogram will it be, obviously the mass of my pen is not changing. All that I am changing is, as we have seen the other day, any physical quantity Q equals to numerical value times units. So here numerical value was N, unit was gram. Okay. Here your numerical value NQ we need to find out. Okay. And U2 is your kilogram. Now, so as we have just taught that the physical quantity has not changed, obviously it also means its magnitude has not changed, and which obviously means your N1 times U1 should be equal to N2 times U2, right? So we know N1, we know U1, we know U2. All that we need to find out is N2. So obviously we can find out N2 as N1 U1 by U2, right? And now let us see what is the physical quantity. It's mass, right? So mass upon mass, right? So here N1 equals to 100, your U1 is gram, and here U2 equals to kilogram. So kilogram we can say 10 to the power 3 gram, right? So which obviously means this is your 10 to the power 2 into 10 to the power minus 3 gram, obviously get cancelled, which is 10 to the power minus 1. So our answer is 100 gram equal to 10 to the power minus 1 kilo. So this is a very simple example I have given, okay, and this would be my continued principle. I would try to explain these concepts by giving very simple examples, and I leave it on to you to go ahead and practice problems and come back, right? Just for understanding, let us take one more very simple direction, okay, and let us try to find out 1 Newton equals to how many dyne, right? So again, what is the physical quantity when we are talking about Newton and dyne? It's force. Okay, give me a moment, guys. We'll use a different pen. So the physical quantity is force. Okay, force. And if I ask you to deduce the dimensional formula of force, what it would be? This is mass times acceleration, right? or n to the power 1, and acceleration is L to the power 1, t to the power minus 2, or this is m L t minus 2. Okay, now let's again go back here. Okay, so n1 equals to 1, u1 equals to Newton, n2 equals to how much, and u2 is 1 dyne, right? So 1 Newton, what is the importance of reducing this dimension? So that I can say that 1 Newton is nothing but unit of mass raised to the power 1, unit of length raised to the power 1, and unit of time raised to the power 1 in any unit. So I can say 1 Newton is nothing but 1 kilogram, right, to the power 1 into 1 meter into 1 second to the power minus 2. Similarly, 1 dyne should be equal to 1 gram, 1 centimeter, and 1 second raised to the power minus 2. Now let's do the calculation over here. Okay. So suppose this is n2, or your n2 equals to 1 Newton by dyne, or as we discussed, mlt minus 2 is the dimension. So 1 kilogram, 1 meter, 1 second to the power minus 2 by 1 gram, 1 centimeter, 1 second to the power minus 2. These two get cancelled. So 1 kilogram I can write 10 to the power 3 gram. This one I can write 10 to the power 2 centimeter by 1 centimeter, 1 gram. So obviously, which means this is 10 to the power 3 into 10 to the power 2, which is 10 to the power 3 plus 2 equals to 10 to the power 5, and that's why we can say 1 Newton equals to 10 to the power 5 dyne. Okay. Similarly, you can do a lot of practice problems. You can deduce 1 joule equal to how many erg, and a lot of those things can be deduced. So I will leave that for practice problems and all. Okay. Now let's move on to the next use of dimensional analysis, and that we call as deduction of physical equations. Okay, so what does it mean? So we know that the physical quantities they are interrelated, in the sense that there are a lot of derived physical quantity which could be expressed as a mathematical formulation of more than one fundamental and other derived physical quantities, right? So here, dimensional analysis and principle of homogeneity can be used to find out what could be a probable relationship between those physical quantities. And please notice the term probable, and the reason I would talk a little later on that. Okay, so let us take an example how we can deduce it, and again I will just take one small example. Okay, let us assume that we want to find out, right, the time period of a pendulum. Okay, say I have attached a pendulum to the ceiling of this room, and I just hit it a bit. So obviously it will start doing the simple harmonic motion, right? So I want to deduce a relationship of what should be the relationship, or what should be an equation for the time period of that simple harmonic motion executed by a simple pendulum. Okay, and here I will start this deduction just with an educated guesswork. So let me denote that the time period of the simple harmonic motion executed by a simple pendulum st. Okay, so obviously when I have attached a string and I have given a tap to it, let me assume that by making an educated guess or by making a logical guess, it looks like probably this time period may depend on the mass of the pendulum, right? So, and let me denote it as m. Okay, it may also depend on the length of the string. Let me denote it as L. Okay, and obviously we know that whenever a substance has some mass, Earth executes its gravitational force on that, right? So it sounds very logical to believe that the time period may also depend on the acceleration due to gravity, and obviously let's use the standard notation g for that. Okay, and let us try to deduce the relationship between these quantities, right? So we said t, when I said t depends on mass. So if I put it mathematically, how should I write? T is proportional to mass raised to the power a, right? Into length times length raised to the power b, and gravitational acceleration g raised to the power c. So which means I can say time equals to some constant k into mass to the power a, length to the power b, and gravitational acceleration to the power c. Okay, now let us apply the principle of homogeneity here, right? If principle of homogeneity is correct, then how many physical quantities we have here? 1 and 1, because obviously we don't have other plus and minus here, and there are only 2 physical quantities here, which means dimension of the left hand side must be equal to dimensions of the right hand side, right? And now let us keep deducing further from there, right? So here when I'm saying time, so I can say mass raised to the power 0, length raised to the power 0, time raised to the power 1 equals to constant k. So we have seen that most of the constants, right, they do not have they are dimensionally neutral, but then it's not a universal thing. So for example, your gravitational constant, it has got dimension. Your Boltzmann constant, it has got dimensions, right? So don't assume that all all constants are dimensionally neutral. So as this sounds to be a pure number, so I can safely assume that this is dimensionless. Okay, now mass to the power a, so I can say m to the power 1, because mass, raised to the power a, length to the power b. So length is nothing but again m0 l1 t0 raised to the power b, right? And g is acceleration. Acceleration is lt minus 2 raised to the power c. So this is where we are. So which would mean I can say here it becomes m to the power a, here it becomes 1, so I leave it, right? So then l to the power b and l to the power c. So I can say it is l to the power b plus c, and then the last quantity is time, so it's t to the power minus 2c. So this is what we get. Okay, now m0, L0 and T1. So obviously by comparing the powers, right, so we can say that we are getting these equations, that A equals to 0, right, and your minus 2C equals to 1, or that implies C equals to minus 1 by 2, and similarly the third equation would be b plus c equals to 0, right? So which implies b equals to minus c, and if we put the value of c from this equation here, so b will be equal to minus of minus half, or that will be half, right? So which means the equation that we got is, it is, your t equals to some constant k into mass to the power 0, right, m to the power a, length to the power b. What is the power b? Is half, and g to the power minus half, right? Which means anything to the power 0 is 1. So, and this is an important thing. If you see, initially we assume that the time period of oscillation depends on mass, and by virtue of doing dimensional analysis, we could arrive at the fact that the exponent is 0, which means, the time period of that oscillation does not depend on mass. So automatically that quantity has got, cancelled out in direction. Okay, so L and G, so we can say L by G root over into some constant k, and we know that, from so this is what we can deduce from the dimensional analysis. And what is the value of this k? Dimensional analysis cannot help you to arrive at the value of k, because it is independent of this numerical value, right? So from our practical experiences, we know that t equals to 2 pi root over L by G. So this is find out from experiments and observations, not from dimensional analysis, right? So that is one of the important limitations of dimensional analysis. So keep a tab on the point, as while explaining the uses of dimensional analysis, we are also touching upon most of the limitations of dimensional analysis. Okay, now before we move on to the pure calculations, let us just spend few minutes to rewind the limitations of dimensional analysis. So as we said, so if I put it in the reverse order, I can say that so it will not help us to deduce value of numerical constants in a physical relationship, right? Then we know that, okay, in the previous equation, we know from our basic understanding of mathematics that if there are 3 variables which we want to resolve with equations, so we know that minimum we should have 3 equations. If you have 3 unknown variables and you have less than 3 equations, ideally it's not possible to reduce the value of those variables from those set of equations. So which means we need at least, right, whatever is the number of variables, at least that many equations or more than that, right? So this is the second limitation, right? Third limitation is again from the principle of homogeneity, that we know that if we are saying S equals to ut plus 3t squared, and if you do dimensional analysis, this one obviously would be your t ut would again be t, and this is 80 squared, right? So this will again be t. So dimensional analysis will say it's correct, but in reality this is not. We know it's ut plus half 80 squared. So using dimensional analysis, we can establish whether an equation is dimensionally incorrect with 100% confidence, and we can say that if something is dimensionally incorrect, that physical relationship must be incorrect in reality. But the converse is not always true, which means if something is dimensionally correct, it may or may not be correct as per the real physical relationship between those quantities. Okay, so these are the basic limitations of your dimensional analysis. Okay, now let us move on to the calculations, so from the calculation part which we have been talking, let us start off with rounding off. Okay, so I will go very straightforward here. I will just talk about the rules that we will use for rounding off. Okay, so we understand that suppose if a particular number is expressed as suppose 12.3141568324976854, it would be very inconvenient for us to express anything in terms of this, and also if you think if something differs by this much of magnitude, it would also not be very much significant until and unless probably you are talking about something of the order of nucleus, right? So apart from that, it would not be important. So many times you would have seen that people tend to round off, right? Round off means, say if I want to round off this digit at this level, and I want to say that I want to round it off after the third decimal point, which means I should drop off all these and find out an equivalent representation where the difference would not be too high. So let us see what are the three rounding principles that we will use. Okay, so first we need to know the digit where we are doing the round off. So the first rule is, if this digit is less than 5, okay, then just drop off this part. Okay, rule number 2. Okay, so here the next digit 1 is less than 5, you can directly drop off this part. If the next digit where we are doing the rounding is greater than 5, so we want to do rounding up at this digit 4, what is the next digit? 1. Suppose if I make it as 7, okay, so the digit where we want to do the rounding, the digit next to that it's greater than 5. In that case, we should drop off all these and we should increase the value of this digit by 1. So the result would be 12.315. In the previous case it was 12.314. Okay, now what is the third rule? We have said less than, greater than, equal to is missing. So if it is equal to 5, then the rule is, so if suppose the digit would have been 3155 and all those things, and we want to round off at this digit 5. So let us go by this initial rules. We move to the next digit. And what is the value of it? It is equal to 5. If it is equal to 5, we need to come back to the same digit where rounding is being done. Okay, I came back to the digit where the rounding is being done. What is that digit? It is 5. If that digit is an even digit, then do nothing, just drop off the rest of the things. And if it is odd, then increase by 1. So here it is an odd number, so I wanted to do rounding at this number. I went to see what is the next number is 5. I came back to the original number. The original number is also 5, which is an odd number, so the answer would be 12.316. I increased 5 by 1. Okay, now let us change it a little bit. Let this digit again be 4. Okay, if the digit is 4 and I want to do rounding at this same digit 4, basic rule, go to the next digit is equal to 5, come to rule number 3. If it is equal to 5, the next thing is to check whether it's even or odd. I will come back to the original digit and check. I came back to the original digit is 4, and here the original digit is an even number. If it is even number, increase it by 1 and drop the rest part of it, right? So the answer will be if it is when it is evening, do nothing and just drop the last part. So the answer would be 12.314. Okay, so this is what it is. So these are the high level things which we should know about rounding off, and using these three rules, simple rules, we can round off any digit which we want. Okay, now let's move on to the next part. Okay, so after rounding off, let us talk about order of magnitude. Okay, so when we talk about order of magnitude, now if we know that when we are talking in physics, when we are discussing in physics, we would be discussing about nuclear physics, where we would be talking about very tiny particles, right? So probably 10 to the power minus 3 would be a very huge number there. So we'll be talking in terms of microns, we'll be talking about even lesser, smaller values than that. Similarly, when we would talk about the universe, right, when we talk about gravitation, we would talk about distance which are in, probably light years, right? So that is why in physics it's very important to understand or to give an idea of the order of the magnitude. Okay, and for our calculation purpose, order of magnitude, this is how we would calculate. So let us write down any number here: 543.4.12347623115. Okay, so this is a number we have written. If we want to know what is the order of magnitude of this number, the simple rule that we will apply is we will express this number into a into 10 to the power b such that a is less than equal to 1, less than equal to 10, which means decimal point should be after the first digit from the left. That is it, as simple as that. So I can put it like this, that this number I can say equals to 5.43412347623115 into 10 to the power 3, right? So I have moved the decimal by 3 digits, and then that's why I put 10 to the power 3. Now, so the order of magnitude of this one, the way we define is, if this number is less than or equal to 5, then say that the order of magnitude is whatever here, so it would be 3. So order of magnitude here would be 3. Similarly, had the number been 6 point something something something, I would have said the order of magnitude is 4, because this quantity we replace it by 10, and 10 into 10 to the power 3 will be 10 to the power 4. So we say order of magnitude as 4. Now there are some authors where we have a difference of opinion that whether we should be contrasting it with 5 or with root over value of 10, which is approximately equal to 3.16. I go by this convention comparison with 5, but then there is a difference of opinion among few physicists who compare it by the root over of 10. So that could be a matter of debate, but I don't want to go into that right here. Okay, so this is where we would end order of magnitude. Okay, and now let us move on to the last part of this first chapter, that is significant digits, or I'll say significant figures and its arithmetic. Okay, so again, what is the meaning of significant figures and errors? I would leave some part of this for you guys getting used to in your lab with the physical instruments, but I would discuss here the pointers which would help you to answer the numerical problems which you may get in your entrance exams. For example, I've seen some numerical questions come up in various medical entrance test exam, in any entrance test exams, and at times in your even in your state board exam or CBSE or ICSE exams. Okay, so I will just be concentrating based on that, and we would learn the calculation part of it right here. Okay, so significant figures. The rules that we will use it, right? Any non-zero number in our calculation, we would count it as significant. Okay. Rule number 2, any number of zeros towards the starting of a number, right, are insignificant, okay, whether or not it's a decimal number or a non-decimal number. Okay, what do we mean by this? So for example, if I'm saying 0, 1, 2, 3, 4, 5, 6, 7, 0, 0. So if I ask how many significant digits this number has, the answer would be 7. Okay. Similarly, if I put 0 point this thing, then what will it would be? Yes, it would again be 7. Though we understand that when we have a decimal point, these do decide the value of this number. I'm not saying they are not deciding the value of this number, but when we are talking in physics and talking about the significant figures, the significance of these zeros are not that high because these are used only to calculate where or to indicate where your this decimal point should be. So if I say if it is that it's 1.2 3, 4, 5, 6, 7 into 10 to the power minus 2. That's it. Sorry, it will be 3. So that is it. So these zeros are non-significant. Okay. So that is the reason why this is how we calculate the. We'll say that the initial number of zeros in any number, they are not significant. Okay. The third rule. Zeros in between non-zero numbers are significant digits. What do we mean? 1, 2, 3, 0, 4, 5, 0, 6, 1, 2, right? Here, the number of significant digits should be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all are significant. So as this 0 is in between two non-zero numbers, this 0 is in between two non-zero numbers, so they all will be considered as a significant digit. Okay, so let's move on to the next point. That okay, so this is in between 0. This is at the starting. This is in between. Now let us talk about what if zeros are the trailing zeros, right? So the trailing zeros after decimal are considered to be significant. Okay, so if I'm writing 12.0, it has got 3 significant digits, and if I put 12.00, it has got 4 significant digits. The reason, again, I will read because we need to understand what is list count and all those things. So that is the reason why I'm not indicating it here. But let's understand the thumb rule that the trailing zeros after decimal, we count them as significant digits. Now, one last thing about finding the number of significant digits is we have talked about in between, before and after. Now suppose if it is not decimal, if we have trailing zeros but the number is not decimal, right? So that is a dicey question. That is kind of a chameleon, and we do not have a perfect answer right looking at the number. So for example, if the number is 5,000, okay, so the only way of knowing how many significant digits are here is we cannot predict by looking at this number. So the person who is asking us this question should express it in terms of the first formula which we saw in order of magnitude, right? So express it in terms of a into 10 to the power b, such that a is less than equal to 1, less than equal to 10, which means we need to put the decimal here. So we can say 5,000 is nothing but 5 into 10 to the power 3. So if the person says it is 5 into 10 to the power 3, okay, in that scenario, if he says if it is 5 into 10 to the power 3, the answer is pretty simple. The number of significant digits is only one, it is 5. If he or she says it's 5.0 into 10 to the power 3, we understand that number of significant digits is 2. If it is expressed as 5.000 into 10 to the power 3, we would understand that number of significant digits equals to 4. So this is how that calculation will be done. Okay. Now, after understanding these things, let us quickly understand the arithmetic part of significant numbers. Okay. So in arithmetic, let's start with multiplication and division first, and then we will go to addition and subtraction. Okay, so I think it will be easier if we solve one example and we will see, because understanding theoretically and then going into solutions it would be a little tough. Okay, so let us do one thing. Let us multiply 24.1232 to suppose 2.0. We want to multiply these two numbers. Okay, so the standard rules that we have in multiplications is, right, the number of significant digits cannot be increased and decreased in the final calculation. Okay, and it should be equal to the number consisting of the least number of significant digits. Now, how many significant digits does the first quantity has? 1, 2, 3, 4, 5, 6. So, yeah, sorry, 5. Significant number of significant digits is 5 here. Okay, and this one, it has got 2 significant digits, right? So, our answer or resultant, right, it should have least number of significant digits in any of these quantities, right? So it should have only 2. Now, so which means after the second digit from the left, we need to do the rounding. So yeah, it's so 24 and 2.0. Now 2.0 has already 2 significant digits, so we need not make any change here, but we need to make changes here. Now the $1,000,000 question is, right, should the rounding of first be done to every single individual number and then multiplication or division should be done, or first the calculation should be done and then the rounding off should be done? And the answer is, first the calculation should be done and then rounding off should be done, for the fact that if we start doing rounding off at every single digit, obviously we would keep introducing those many errors in those many calculations, right? So first multiplication or division is done, and then finally the rounding off is done. So if we multiply these two, it will be how much? 48.246. Now, using the principle of rounding off, I need to know this is the first significant digit, this is the second significant digit. My answer should have only 2 significant digits, which means I need to do the rounding right here. If I need to do the rounding right here, what is my principle? look at the next digit where we want to do the rounding. The next digit's value is 2. If the next digit's value is 2, then obviously it is less than 5 and I should be dropping this, right? So which means it should be 48.0. Now the question is, should the answer be 48.0 or 48? Yeah? So, and the right answer is, this is wrong, this is right. Though numerically they are not different, but as per significant calculation this is right. For the fact that the rule that we have established is your answer or resultant should have only as many significant digits as in the quantity with least number of significant digits. So least number of significant digits here is 2. So your answer should not have more than 2 significant digits. If you write the answer 48.0 as per rule number 3 or 4 which we saw earlier, it has already got 3 significant digits, so it's wrong. Obviously, if you write 48.00, it's obviously wrong because you have introduced 4 significant digits. So that is what we need to keep a track when we are doing the multiplication and divisions in line with the significant digits. Now, let's go to the last part, that is addition and subtraction. Okay, addition and subtraction. So here, couple of principles are same, that the answer should have, the resultant should have the first significant or the least significant digits after the decimal. So we need to stack them up one above the one below the other with the positioning of the decimal, and wherever after decimal is the first doubtful digit, after that everything should be dropped off. Okay, and here one difference is, unlike multiplication and division, first rounding off is done and then additions are done. So for example, if we want to add 23.1506 to 6.42, right? And suppose we want to add 0.2. So in this situation, right, I have stacked them, one below the other as per the decimal number. So here the rounding off should be done for each of the digits. Okay. So if I do the rounding, what will be the equivalent? So it would be 23 point. I need to do rounding here. I need to go to next digit. Next digit is 5. If next digit is 5, I need to come back to the original digit. Original digit is 1, which is an odd number, which means I need to increase it by 1. So after rounding off, it becomes 23.2. Now let's go to 6.42. I need to round off here. I will first go to next digit. This is less than 5. Less than 5 means I need to drop. So it will be 6.4. Here I need to round off at 2. So it will be directly 0.2. Now if we add them, this is 2 plus 4 plus 2, 10. I get 1 here and this becomes 30. So the answer is 30.0. Don't make it 30, this is wrong, or don't make it 30.00, this is wrong, or obviously not 30.000. Okay, so here we would come to the end of the first chapter, unit dimensions, and obviously our next chapter we would move into would be scalars, vectors. In the meanwhile, I'm starting my online classes for class 11 students from this coming Saturday, that is 20th June 2020 at India time 12 noon. So if you want to join my classes, because obviously in a recording video we cannot have interactive discussions and we cannot solve a lot of practice problems. So for that, you may write to me at Rajiv, CAPRAJIV 34 at gmail.com, or this is my number 998-580-7815, and I stay in India, so my ISD code is +91. So you may call me up on any Saturday or Sunday between 9 a.m. to 9 p.m. IST, or any other working days. If you want to call me, I will have a very small window that would be from Monday to Friday. If you want to call me, it should be 6 p.m. to 7:30 p.m. India Standard Time. So this is my information, contact information. So I repeat, I am starting my online physics classes for class 11 students from 20th June 2020. As I have said in my previous videos, it is 100% free of cost. So I'm not gonna charge even 1 rupee to any student, because as I said, this is my passion, and I just want to relive my passion. What I did 15 years back, I want to restart that. I want to start teaching students again. So if you want to be in touch with me, please connect to me on either on my mail ID or my phone at the given times. So thank you, students. So we will be loading the videos for the next chapters in next few days. Stay tuned till then. Bye bye.